Good evening, sir.
Okay.
Good evening, sir.
Good evening, sir.
Good evening, sir.
Good evening, everyone. And yes, good evening, people.
Also, like,
अरे पूछो मत, but honestly I'm very happy in a way today that the kind of support I received from the other end, from the management. So एक तो ये last minute, literally 1 minute before, there was a short circuit here, and then obviously so I was helpless. But yes, they told us that it should be sorted very soon. So I asked them that if at all class could be swapped, but then Neeraj said that sir, I can start at 5:45. I'm like, sir, okay, you take from 5:45 to 7:15. I will take from 7:30 to 9. But let us take a class today itself because I don't want us to use any additional day. I want to give you one complete month, people. If we would have cancelled today's class, then we would have had to take a lecture on Friday or Saturday necessarily. So I want to give you a complete month from Friday onwards. I'm like, sir, no matter what, let's take 1.5 today. So I started 7:30 to 9. I don't mind at all, and I don't think my students will mind too. They mind people 7:30 to 9.
No, sir.
No, sir. Contact with the
Chalo, good that. I mean, still, but the only reason is so that they don't have to extend the lectures beyond Thursday, nothing else. So anyway, let's continue, people, with our derivation of this. By any chance, did you guys check out the C1? That we'll be doing that in the class. So anybody here, did you get the result? So we were studying two equations. We had got two equations yesterday, and the equations were. Let me just remove this and add this. But I appreciate the management's work. Like they sorted everything very quickly in 5, 10, 15 minutes, but it was done nicely. So kudos to them. C1 plus C2 people, that's C3. And that was the equation that we had, first equation. And another equation was C1 minus C2 was K2 upon K1 of C3. Can you just confirm these were the equations, people?
Yes, sir.
Okay. So I had asked you all to express C3 in terms of C1 and C2 in terms of C1. The reason was logical, that actually C1 is nothing but the amplitude of incident wave, C2 was amplitude of reflected wave, and C3 was amplitude of transmitted wave. So we wanted reflection in terms of incident, and we wanted transmission in terms of incident. Okay. So there are multiple ways in which we can go about it. So first of all, we can add them directly. How about just adding them? So if we add people, then what happens? C2 minus C2 gets cancelled. The remaining 2C1 is C3 plus K2 upon K1 of C3. Huh? So I can say 2C1 is, you can take C3 common, you're left with 1 plus K2 upon K1. So what are we having, people? 2C1 upon 1 plus K2 upon K1. This is C3. Okay. Or I can say 2C1 upon cross multiply K1 plus K2 upon K1. This is C3. Or I can say 2K1 upon K1 plus K2, the whole into C1. This is C3. Okay. People have expressed C3 in terms of C. I just give K1 in the numerator. No? Denominator of denominator is numerator. So I just give K1 in the numerator and written C1 separately outside. Okay. You have expressed C3 in terms of C1. Copy this, please. This is the first slide, people.
copy, sir.
Let's other copy. Others, take a time.
Copy.
अच्छी बात है. चलो. Next. Let's also write C2 in terms of C1 now. For that, you can substitute C3 anyway. Let's substitute C3 in equation 1 or substitute C3 in equation 2, wherever you want. Obviously, you will prefer to substitute in equation 1, people. So what is equation 1? C1 plus C2 is C3. You can always select the right. So people, we want to find C2 now, right? So C2 is C3 minus C1, okay? So C2 is C3. Why is it not taken off the pen? C3 minus of. Weird. Okay. Sorry. C3 minus C1. Why is the pen not taken off from all of a sudden?
Chai bhi thi, sir.
Let me just okay. So anyways, C2 is C3 minus C1. What is C3? So C3 is 2K1 upon K1 plus K2. 2K1 upon K1 plus K2 into C1. That's C3. No, I just substituted C3 people there. Okay. So C2 is, let's take C1 common. You're left with 2K1 upon K1 plus K2 minus 1. So C2 is C1 into 2K1 minus K2, the whole upon K1 plus K2. I just expanded now. Cross multiply. Minus 1 into K1, that's minus K1. Minus 1 into K2, that's minus K2. So C2 is C1 into, what do we have? I hope you're on correct track. 2K1 minus K1, that's K1 people. Yes. So K1 minus K2 upon K1 plus K2. That's C2 people. We found out C2. So C2 also is found out in terms of C1. C3 is also found out in terms of C1. This is K1 minus K2. No? 2K1 minus K1 is K1, and then you have minus K2. Written, people?
Yes.
Yes, sir.
Okay. So now what? I had made you write and recall that intensity is proportional to amplitude square, people. First thing. In our chapter, instead of writing amplitude square, we can write amplitude star amplitude just in case amplitudes are complex, which they can be. Next. Then, for example, we have learned absorption coefficient was amount of heat absorbed upon amount of heat incident. You know? Very similarly, instead of writing absorption energy, what we can replace it with amount of intensity absorbed upon amount of intensity incident, because intensity and energy are also directly proportional. Intensity is energy per unit area per unit time, people. Intensity is energy per unit area per unit time. Okay, so we can energy replace Q also with I, they are also directly proportional to each other. So this is how we generally define basically coefficients, absorption coefficients. Right now, we don't have any absorption, it's just a normal boundary, people. But there is reflection that could be possible, there is transmission that could be possible. We are not considering any absorption here. So in that case, when you write A plus R plus T, which is 1, no absorption, people. So there is only R plus T, that should be 1 basically. Okay. In quantum, what we are going to do is we'll use capital coefficients, people. So this is just for your understanding. Okay. Everything here is only for your understanding. So coefficient of reflection, that is capital R. Coefficient of reflection, that's capital R. So very similarly, it will be amount of, you can say heat reflected upon heat incident, but rather we will write amount of intensity reflected upon amount of intensity incident, people. Okay. But intensity is directly proportional to amplitude square. Okay. What is amplitude corresponding to reflection? C2. Okay. For incident, it is C1. Reflected, it is C2. Transmission, it is C3. Okay. So this is nothing but C2 star C2, and this is nothing but C1 star C1. Okay. So let's calculate this. And similarly, transmission coefficient would be IT upon II, and this will be transmission is related to C3. So C3 star C3 upon C1 star C1. Intensity is proportional to amplitude square, which is A star equal. So IR is C2 star C2, IR is C1 star C1. Okay. Make a note. You can ask me if you have any questions. Do not hesitate. ठीक है?
Yes, sir.
Let's calculate. Let's start with R. So R, which is C2 star C2 upon C1 star C1. The best part is all the coefficients are real actually. Okay, C2 is also real and C1 is also C3 is also real. C3 is also real and C2 is also real. So now you can actually write it as C2 square upon C1 square directly. The reason you can write only because they are real. Because they are real. Okay. So what do we have? C2 square. Huh? Okay. So if we square this, where is this guy? So if we square this, I have a small concern. I'm just
सर
thinking.
C2 upon C1 कर लो ना
नहीं वो तो हम कर लेंगे. I'm not thinking that if we square this we'll have K1 minus K2.
सर आंसर नहीं आएगा मैंने किया था
किया ना था because यहाँ
yes
पर
sir 2
K2 is
K1 K2 आना चाहिए
हाँ K2 is missing somehow. K2 is missing somehow. That also I can think. Here so it's fine. Let me just check. Actually, there is another thing which we can always use, but that becomes a very long way. So I've taken a shortcut. To be honest, I've taken a shortcut here. But because even K2 नहीं आ रहा है, that's the sad part. बोलो ना.
सर मैंने YouTube पे चेक किया वो सर जैसे अपन R कैलकुलेट करेंगे ना तो उसके लिए K1 upon K1 करते हैं और T के लिए
K1 upon K1? No, it's not that term. Actually, I know the correct root of this, but that is a very elongated root. Actually, we have to write probability density, probability current density, JR, that was J form experiment we had learned, which was I think something like h squared upon 2im psi star del psi minus psi del psi star. But that becomes a very long root. I did not want us to take that root, but using that we will get the result. But why here we won't get that mystery? But we should be getting. I will just check this. Give me 1 minute. Using that we will get. There is no problem whatsoever. But it becomes a very elongated root. But what's doing? I mean, the whole derivation is completely worth doing if we go to that root. Okay, so for example, eventually they are getting C2 star upon C1 star, that's good. And no. What would one type people have? There is okay, so we learn here there is only a specific case, there has to be a specific case where they are allowed to use. So the thing is using this shortcut trick, the value of R is we are going to get correct, but value of this transmission coefficient we will get incorrect. Okay, so एक elongated root हमें अपनाना है. We'll take a long root. And leave this. So this definition, don't say it's incorrect, just write this is not always correct. When it is correct, we will learn. This is not always correct.
So which definition of the coefficient reflection transmission?
Yes. This is not always correct. Just write it back. Just write it. This is not always correct. Yeah. Chalo. So I've divided this. So now what is the next definition we are supposed to use? See, so now the derivation increases in its length, but it's okay. It's completely worth doing. Okay. So the reflection coefficient, what we can do is it's also defined as the probability current density JR upon probability current density JI. Okay, JR is basically, I hope you remember how to calculate J. Any probability current density, we have written this formula earlier. It was h squared upon 2im into psi star del psi minus psi del psi star. Do you remember this? Okay. That's what we have to use. The difference will be for in case of R, you have to use the R wala wave function. For I, you have to use I wala wave function. For T, you have to use T wala wave function. So it becomes obviously an elongated process. But okay, let's see. And then we will eventually realize that where exactly we are going from. Okay. So transmission coefficient, the general definition of this is which is JT upon JIP. Okay, make a note. So this is always correct. This definition is always correct.
JR is the probability current density
reflection
of reflected wave.
Of reflected wave, yes. And JI is probability current density of incident wave. JT is probability current density of transmitted wave. This definition is always correct. People many a times doing a mistake, obviously not in the exams, before the exams, is like a blessing in disguise because once you have done it, you will remember it. So even when you give tests, mock tests, etc., if you commit mistakes, don't be sad about it. In a way, be happy about it. Obviously, committing mistakes is not good, but at the same time, see the silver line. See that now that you have committed that mistake in our class test or in your assignments or wherever, that will be hammered in your head and you'll be like, okay, now I cannot repeat this. And you will, otherwise, what would have happened if that mistake you wouldn't have done here? Suppose that question was not there in this exam, and if you wouldn't have done that mistake, then what would have happened? You would have committed that mistake in the exam, in the finals. So right now, for example, if I would have refrained from doing the derivation, I would have been like, that happens. Okay, you need to remember C2 star C1 upon C1 star C2 star C2 upon C1 star C1, you get the answer after C1. But then we would have assumed that is always correct. Okay, but now that we committed from the same, now we know it is not always correct. This is always correct, absolutely. So we will learn the case that when that will be correct. For example, in Newton's cycle, remember we learned that F equals to ma is not always correct. It's correct only when mass is constant. If mass is not constant, then we have an additional thrust force, which is given by dm by dt. Okay, so we discover things with time. Consider these things as blessings in disguise. Proceeding ahead anyway. So to start with, what were our wave functions, individual wave functions, people? Psi I, that was C1 e raised to I k1 x. Then psi R was C2 e raised to minus I k1 x. And psi T is C3 e raised to minus, just I k2 x. The thing is, the place where we are going on, why it is not correct is propagation constant is changing people. For reflection answer you are getting better. As you see, like the calculations that we did, okay, C2 in terms of C1 and everything. For reflection answer is K1 minus K2 the whole square upon K1 plus K2 the whole square, which is fine. For transmission you are not getting the answer because the propagation constant changes. For reflection it doesn't change, but here the propagation constant actually changes. That's the only problem. Maybe I can give you a cheating method here. I can just say that multiply, like, if you want to use C2 star C2 upon C1 star C1, if you want to use that, we should multiply by the respective propagation constants too. That way we will immediately get the answer also.
सर यही मैं कह रही थी उस टाइम.
But that's manipulation, no? It's not. So like we know that that is going to happen, and hence we are doing that manipulation. We can multiply by this. But okay. So you're basically also saying that whatever was our answer, we have to multiply and divide by K2 upon K1 and whatever K3 upon K2. So but let's take this process. It's not a bad process to also follow. Anyway, so let's get started. Okay, I hope you remember this. We have written this in the class. So to start with, we first want to calculate one thing after another. Let's start with JI. Okay, let's calculate JI. So that's whether you can least worry about x upon 2i. Why? It will get cancelled now for all of them. So don't worry about this at all. Okay, let's just focus directly on this. Okay, so I'm just going to write it is some let me write it, but it's not important. That's what I mean. Okay. So this is psi I star. Del is dou by dou x. Okay. Into psi I because it's 1D now. And then minus psi I star. Psi I dou by dou x of psi I star. Psi star del psi minus psi del psi star. That's what. But instead of del, you are writing the partial derivative with respect to x because it's 1D. Now it's just a horse work, nothing else. Okay. So behave as if you're a horse and keep on running. Okay. So psi I, which is c1 e raised to I k1 x. C1 e raised to I k1 x. But people, this is star. Conjugate means you have to write this minus. Okay. Dou by dou x of c1 e raised to I k1 x minus c1 e raised to I k1 x dou by dou x of psi I star. This c1 e raised to I k1 x. But the thing is, this is conjugate, right? So we'll like minus. It's only horse work after this actually. It's not. There is no physics in this. Purely mathematics actually. So I will see. I mean, we may not need to do everything, but let's look. So what do we have? So by the way, also if you want, you can write c1 as c1 star also because it's conjugate now. So c1 actually becomes c1 star. Here also when we conjugate, so c1 becomes c1 star. But all of this is only formality. But okay, let's obey the formality so that you will have a book where you're writing everything. First of all, ask me if I have any problem in this step, people. I hope you understood. When we take conjugate, you have to write c1 as c1 star and I becomes minus I. And here also c1 as c1 star, I becomes minus I. Now it's time pass work. So what do we have? c1 star e raised to minus I k1 x. Here what do we have? c1 into. Again, what we will have? What is derivative of e raised to x? That's e raised to x. But you have to redifferentiate this. If you redifferentiate this, what do you have? I k1. Similarly here also, c1 e raised to I k1 x, c1 star outside, derivative of e raised to x is e raised to x. It's not a difficult part at all. It is just a tedious part. Okay. And what is if you redifferentiate this, what do you have, people? Minus I k1. Okay, no problem. So what do we have? As we clearly see, e raised to minus I k1 x, e raised to I k1 x gets cancelled. Okay, and we further have h cut upon 2 which is only a formality once again. C1 star C1 also you can take common, people. So if you take C1 star C1 common, what are you left with? I k1 minus plus I k1, which is 2I k1. Got it? Any questions? Anyone? Okay. C1 star
So
C1
can we take C1 as constant, real constant? Is it necessary that?
See, we don't know whether it will be real constant or not.
It's an amplitude.
No, it's not necessary. Amplitude could also be our complex. That's not a problem. But the thing is, now it will be constant because we have a relationship now. So C depends only on K. So K is not complex. So here you can claim that it will be real. But okay, like I said, it's a formality. It's complete formality. But no worries. Yeah. Now I can use at least who looks similar to this. Psi doesn't look similar, but Psi looks similar. No? Complete similar, people. C1 is replaced by C3 and K1 is replaced by K2. So I can at least save some of my time by using my favorite word similarly here, and that is JT, people. What will that be? H cut upon 2IM. H cut upon 2IM into. Instead of C1 star C1, you will have C3 star C3. You will have everything is identical. And instead of 2I K1, you will have 2I K2. I hope you realize now you will take the ratio, you have that additional K2 by K1. Okay, right?
Yes.
So this is how the K2 by K1. But the YouTube wala they must not have explained why the K2 by K1. Did he explain that?
सर दूसरी वीडियो में था.
Anyway, so let's calculate GR. GR we may not have the same idea because there is a small change in that. I think we'll have minus in GR probably. Let's check. So what is GR? H cut upon 2IM into psi star del psi del which is dou by dou x psi minus psi del psi star del is dou by dou x of psi star. But you have to write reflected function. Actually, I thought that it will be large in derivation. It's not that large one. But we did it quite easily and quickly. I thought it will consume more time, but no, it's only 5 minutes. Happy. Okay. So psi r star people, which is c2 e raised to minus I k1x. Okay. So this becomes c2 e raised to minus I k1x. But the thing is, that's only psi r. This is the value of psi r. Okay. But first you have to write psi r star. So this becomes c2 star and this becomes plus. Okay. Derivative of c2 e raised to minus I k1x minus c2 e raised to minus I k1x dou by dou x of c2 e raised to minus I k1x. But here again you have star, so c2 star and this becomes plus, people. I hope you have understood this much. But have you copied the previous one? Copy the I don't know, people. If anybody's like, let me know.
Copy sir.
Others also please let me know. Okay.
Copy, sir.
Okay. So copy this JR. It's not that lengthy. I thought it would be lengthy. It's not lengthy. Okay. Unnecessarily I scared you. You know? Okay. So what do we have, people? GR. I think we have, but we will have a minus sign this time. So GR would be h cut upon 2IM into c2 star e raised to I k1x, c2 star e raised to I k1x into c2 you can go outside. Derivative of e raised to minus I k1x, that's e raised to minus I k1x, but you redifferentiate this, you get minus I k1 additional term. Okay, minus again we have c2 e raised to minus I k1x, c2 e raised to minus I k1x. Again, if you redifferentiate, take c2 star outside. So if I take c2 star outside and derivative of e raised to I k1x, that's again e raised to I k1x, but redifferentiating this gives us I k1 additional term. So again, like last time, these two terms are getting cancelled, these two terms are getting cancelled, and we are getting JR is h cut upon 2IM into. You can again take c2 star c2 common. What are you left with? Minus I k1 minus I k1. You have minus 2 I k1. So like I said, the only difference here I did not use similarity because I knew that it won't be exactly identical to have an additional minus numbers. Okay. Actually, you know, we could have been a little smart. You know how? Can I write for an example? Temporarily, this says c2 e raised to minus I k1 as I into, let's say, some k alpha x, where k alpha is minus k1. Now I can do similarly, and at the very end, I should have replaced k alpha with minus k1. Did you understand?
Yes, sir.
Yes,
We are looking at it.
We should have just replaced k alpha with minus k1. Okay, but okay, we learn things as we proceed. But this could also have been done. We should not have calculated GR. You could have used the word similarly, but just replace k alpha with minus k1. Okay, so in that case, here you would have got.
How do you know before the calculation?
Yeah.
How do you know that before the calculation?
What before calculation is that we will have a different answer.
Minus alpha, that is how do you know?
No, not I know. The thing is, this is I k1x, this is I k2x. This is positive, this is positive. So we just what did we do? We calculated. We use similarly for psi t. Why did I use similarly for psi t? Because c1 is replaced by c3, k1 is replaced by k2.
Yes, sir, that's okay.
But here the thing is, what we could have done is these are positive values now. So I don't want negative sign. So what we could have done is you can just write this as e raised to I some random, right? K alpha, k beta, whatever you want to write. It's just a coefficient. Where k alpha is minus k. You are just writing it that. Now it looks similar, no? Again, replace c1 with c2, replace k1 with k alpha. Understood? But in the final answer, we'll again replace k alpha with minus k. Understood?
Okay.
So that's how we could have done that. So like we could have got this and then anyway, but leave it. So this is already done, calculated, doesn't matter. But still, even if it is already done, you should know that there could be a time saving. ठीक है, चलो let's calculate. So what is our coefficients people? Let's also put mod up because these are coefficients, so they are magnitudes people. Please put mod. Please put mod. Okay, sorry, done. Shall we next? Okay, here we go. So I think now we got the result. So R is equal mod of JR upon JI. So this is what is JR people? H cut upon 2 IM C2 star C2, H cut upon 2 IM C2 star C2, okay, into minus 2 IK1 minus 2 IK1, the whole upon what is JI? H cut upon 2 IM C1 star C1 into 2 IK1 people. So what do we have? H cut upon 2 IM, H cut upon 2 IM gets cancelled, 2 IK1 gets cancelled, minus doesn't matter, there is any magnitude, you just have C2 star C2 upon C1 star C1. See, we have already know that they are real, you can write C2 square upon C1 square, and now we have the answer which we already knew. This we were already writing now. This was our first assumption. Okay, so anyway, the answer this one is already ready. What is C2 square upon C1 square? Here, C2 is C1 times this now. So what is C2 upon C1 people? K1 minus K2 upon K1 plus K2. So that's it. K1 minus K2 the whole square upon K1 plus K2 the whole square. The only thing is I assume that this is always 1. It is valid as far as medium is same here. If medium is changing, wavelength is changing, propagation constant is changing, things will change. Things will change actually. But that's okay. Anyway, K1 minus K2 upon K1 plus K2 the whole square. Understood everyone?
Yes, sir.
Yes, sir.
Great. Next, proceeding ahead. R is okay. Let's calculate T. That's JT upon JI. So this is equal to H cut upon 2 IM. This is what is JT? C3 star C3 into where is JT? 2 IK2 into 2 IK2. The whole upon we have H cut upon 2 IM. I would have written C1 star C1, 2 IK1 respectively. And as we see people this time, these two get cancelled, 2 IY gets cancelled. Our answer is C3 star C3 upon C1 star C1. That's fine, but just that there is an additional multiple of K2 upon K1. So this is where we were not getting the result in the previous case. The reason is medium change now. But the best part is in exam, now you know what to do. You don't have, you will never use JR JT wala formula. You'll always use this. All you have to do is divide by the respective medium star propagation cost. That's what you always have to do. Okay? So this is just C3 square upon C1 square into K2 upon K1 people. Okay? So C3 square upon C1 square. What is that people? So what is C3 upon C1? Where is it?
2K1 upon K1 plus K2.
So C3 upon C1 is 2K1 upon K1 plus K2. You already have that. Okay? Yeah. So C3 upon C1 is 2K1 upon K1 plus K2. Let's substitute that. So what do we have? 4K1 square upon K1 plus K2 the whole square into what do we have? K2 upon K1. K1 square gets cancelled. Outstanding. We got transmission coefficient is 4K1 K2 upon K1 plus K2 the whole square. Beautiful. Nice. Great. Any questions? Anyone? Anywhere? Please ask. Okay, everyone? Shall we?
Sir, 1 minute.
Take your time. So now we just cannot say density is proportional to amplitude square if the propagation constant is changing, if wavelength is changing. So now I'm curious, So actually the thing is, when we talk about optics people, where we use intensity is proportional to amplitude square all the time, we have used it in interference now. So now it's not always correct. And why do they don't mention it there? Because they're what intensity they're talking about all the time. Intensity of right band, dark band, intensity of first slit, second slit, but all of them is happening in the same medium all the time. So medium is not changing there. So they're least worried about the fact that it should be multiplied by K2 upon K1 or lambda 1 upon lambda. No, K is inversely proportional to lambda. So they would have written lambda 1 upon lambda. But they don't teach it that. Even in oscillation waves also, in sound wave structure, you may have used it. Intensity is proportional to amplitude square. But again, there also everything is happening in the same medium, so they are least worried about it. So this is a very important learning for her actually, where we realize intensity is proportional to amplitude square. That's fine. But at the same time, it is inversely, I think directly or inversely. What is the relation K2 upon K1 is here? This is technically IT upon II. So it's directly proportional to K. IT has K2, directly proportional to K, but inversely proportional to lambda. It is inversely proportional to lambda. Okay, so this becomes a more general form, right? Make a note, like for your understanding only, for optics. Okay, it's directly proportional to K, but it's inversely proportional to lambda. Hey, hang on. Sorry, I'm thinking something. In electromagnetism, you have that intensity of formula 1 by T, 1 by 2, T something. What is that?
1 by 2 C epsilon not E square.
C epsilon not E square. Okay, but no. I was thinking that they are connected or not. C can be written as that number, but that could make it no. But that frequency is also there as a function. Absolutely. Just thinking by any chance if that was corrected there. But okay, no, maybe we don't know. Shall done people? Next. Okay, so R plus T. Let's take R plus T. There is too much of noise. Too much of noise. You tried to unmute a couple of times before, but I couldn't hear again. So R plus T people. Okay, what is R? By the way, you are supposed to have these values of R here forever. So R is K1 minus K2 the whole square. Okay, K1 minus K2 upon K1 plus K2 the whole square. That's R people. And what is T? T is 4K1 K2 upon K1 plus K2 the whole square. Okay, so what do we have? A square minus 2ab plus b square plus 4k1 k2 the whole upon just keep k1 plus k2 the whole square as it is.
Sir, 4k1 k2 upon k1 plus k2 का whole square. 4k1 k2 whole square से बाहर.
Yes, I mean I wrote it correctly here, but yes, absolutely. Okay. So 4k1 k2 upon k1 plus k2 the whole square. And here also what we can do is we can split the brackets. That's best. You can write it's actually k1 minus k2 upon k1 plus k2. They are the whole square, but here just split the brackets. So that's best. So denominator is same now. Since denominator is same, you can just add the numerators. So if I can add the numerator a minus b the whole square, that's a square minus 2ab plus b square, and then we have 4k1 k2. Okay. So what do we have? K1 square. People 4k1 k2 minus 2k1 k2, which is 2k1 k2. 4k1 k2 minus 2k1 k2, which is 2k1 k2. You have k1 plus k2 the whole square. What is this? A square plus 2ab plus b square. We got the answer k1 plus k2 the whole square upon k1 plus k2 the whole square. Congratulations, everyone. R plus T is 1.
We have discovered something.
Yeah, what
very
is
interesting.
What does it
Yes,
imply?
sir.
Coefficient reflection, coefficient transmission. Those,
Same here, R plus T is 1.
yeah, that's what I'm thinking. What does this imply?
But nothing. We learned that R plus T is 1, but absorption coefficient was 0.
Absorption coefficient is 0.
So only reflection and transmission is happening. That's it.
Okay.
That's it. So we proved it basically. We proved it.
So this formula for reflection coefficient, transmission coefficient, कहाँ use होता है?
This formula is R plus T equals to 1.
No. You said that you have to remember this coefficient of transmission and reflection.
For this case, for the case that we learned.
Square wave.
Square
One
wave.
step potential.
Barrier potential or whatever we call step potential.
Step
Okay.
potential.
Yes. Okay. But this thing that we learned, this was the discovery of like nice. Okay. But anyway, please ask me if you have any questions. Okay. Sure. Nice. It's okay. It was worth our time. Completely worth. So now what we are supposed to do? We complete step potential here, but the case one we have completed. Okay. I hope you remember there was an assumption at the very beginning. E was greater than D. Now we have to take case two. It's an altogether new problem. Don't you think it's a continuity? So one problem is there. So now there is an altogether new problem, but it is step potential only, but where E is less than D. Okay. So please give any case two. But now we will go it very quickly. But others, do you have any questions right now or any confusion in any of the formula? So the general idea is that the reflection coefficient always you have to write mod of GR upon GI, okay, and the transmission coefficient always you have to write JD upon GI. However, if you want to use the shortcut, whenever you can write C2 star C2 upon C1 star C1, but you have to also multiply by the respective propagation constant. So here, remember, reflection happens in first medium, so K1. Incidence happens in first medium, so K1. So K1 gets cancelled. Shortcut I'm trying to tell you. And here also you can write C3 star C3 upon C1 star C1, but the thing is, transmission happens in second medium, so K2, but incidence happens in first medium, so K1. But here they won't get cancelled. I would have directly, done some cheating and made you understand like this, but I think because we discovered that's even better. Okay. So, but this is a bit shortcut to remember. Note if you want. And the final answer of RNT. Okay. But this formula is always right. This idea you can use not only in this. What do you say? Oh no, wait. We'll talk about it. No, it depends on wave function. It absolutely depends on wave function. Okay. But as far as the wave function of plane wave and step potential, we can use that, right? Okay. And after C is absolutely 1, so that's also fine. And the value of R you have to remember, value of T you have to remember. K1 minus K2 to the whole square upon K1 plus K2 to the whole square, and 4 K1 K2 upon K1 plus K2 to the whole square. Okay. And actually, in a way, it's good that I was again doing the whole square stuff. We did this because we technically took a good example on probability current density. What if they ask a question on that? So it was like a good revision for probability current density. So done, people. Shall we next? Okay.
Yes, sir.
Let's proceed. Case 2 for this time. Okay. So now the case is E is less than B. Let's do this. So V of X, we have got X. Okay. And let's say the complete left region is 0, and then there was a sudden jump here, and then it becomes constant. The constant value is V0. Here you can write here basically Vx becomes V0 in region 2. Okay. And here Vx was completely 0 in region 1. In region 1. Okay, this is origin 0, you can write it. Now what we have last time, because we had taken energy was greater than V0. And what is it that I had told you? Classical mechanics will predict that this will always be transmitted, but quantum mechanics tells us that transmission is possible. And by the way, we found out transmission coefficient. Another thing is quantum mechanics gave us transmission coefficient. We got the value 4 K1 K2 upon K1 plus K2 the whole square. Remember that will be very, very, very small. It will be very small. 4 K1 K2 upon K1 plus K2 the whole square. Yeah. Comparatively, like in fact, it should be something like one will be 0.96, other will be 0.04. This will be the difference in reflection and transmission. Reflection coefficient will be very large, transmission will be very small. Total will be 1, but yes, the numbers will be very small usually. Okay, for transmission. And because the probability is very small, it cannot happen all the time, but some probability still exists at quantum mechanics exists. Now the story is energy is less than okay, V0. Energy is less than V0. Okay, so classical mechanics prohibits transmission again. Quantum mechanics again allows transmission. That's the same part. Okay, classical prohibits transmission. Okay, but quantum mechanics allows transmission here. Okay, and initially, previously the story was sorry. I think I may have misinterpreted, or I think I may have said it wrong. I'm not sure what did I say before. Did I say transmission was prohibited in the earlier case?
Yes, sir.
Classical was saying that transmission is allowed, but reflection is prohibited. But this guy. Quantum tells us that even when energy is greater, reflection is possible. Okay, quantum tells us even when energy is greater, it can still be reflected back. Okay, so when I give you the example, 0.96 is the transmission probability in that, and like 0.04 would be the reflection probability. Actually. Okay, you can always correct me if I say something wrong. You don't have to wait. Confused नहीं होने का बोलेगा sir. I'm confused. Can you please repeat? Okay. Anyway, we just have 2-3 lectures left, people, but still. Okay. Chalo. I hope you understood now the confusion is sorted. Okay. Quantum allows transmission. Okay. So what next? Sorry, the equation. I hope you read the diagram.
Yes, sir.
Let's apply Schrödinger's equation. Here we go. So our direct equation is t square psi upon dx square plus 2m upon h square into e minus v psi. This is 0. This side, in case 2, in this case, the value of v. Okay. So we have to take reason by reason. Let's first talk about reason 1. I think reason 1 is not changing at all. What happens in reason 1, people? We have x is 0. So what do we have? D square psi upon dx square plus 2m upon h square into e minus 0 into psi. This is 0. But purpose what we will do is to write psi as psi 1 for reason 1. Okay. So we have got d square psi 1 upon dx square plus 2me upon h square psi 1. This is 0 because this is exactly the story of last time. In fact, we've done this 4 times already in free particles. Then after that in 1D box in last case and even now. So the same old story. So we can just start with let k1 square be equal to 2me upon h square, and then I will just write done before. Okay. What is the final answer of C1? Psi 1. Final answer. It was just C1. But no, we will not write cos sign for it. We'll use the previous case only. What was the answer? C1 e raised to I k1x plus C2 e raised to minus I k1x. I hope everybody you're fine with this. Okay. Because nothing is different. Nothing is different from the previous case. Okay. Nothing is different. Done before in case 1 you can write. In case 1, everything is same. Okay, call this equation 1. Please tell me if you have any questions. Don't hesitate. Okay. Good. So yeah. Next, proceeding ahead. Let's calculate psi 2 people. Reason 2. Okay. I hope you have copied the second right. Reason 2. Now the story changes a lot. Okay. How exactly? In reason 2, V is V0 and energy is less than V0. You need to remember. Just remember, e is less than v naught. Not in region 2, but e is already less than v naught, and in region 2, v is v naught. So our value d square psi upon dx square plus 2m upon x square, which is into e minus v psi. This is 0. What are the changes, people? First we'll write psi 2. We'll write psi 2. Okay. Okay. E minus v naught we can write, no problem. This is 0. If you think, but sir, this is also same as last time. No, people, there is a major difference. Now who is greater? V naught is greater now. Okay. So you have to shuffle them. You have to take minus common. Now we have to shuffle them. V naught is greater. Okay. So let's take minus common. What do we have? 2m upon x square because v naught is greater. Okay. I did nothing. Simple. I have just taken minus common. E minus v naught equals v naught minus. The only reason is now you throw it on RHS people. What do we have? D square psi 2 upon dx square. This is 2m upon x square into v naught minus e into psi 2. Or wait, sorry. Hang on. So what we can say is, I'm thinking something. So now that, because the propagation constant cannot be negative. The propagation constant, that's wavelength, that cannot be negative. So why did I do this? Because tell me one thing, if you would have said k2 square is this, people, e is less than v naught. K2 square would be negative. It will become complex. Doesn't make sense to us. Wavelength complex, whatever. No. So you cannot write k2 square is e minus v naught. I hope you understood that first why I had to do a small manipulation. And now you can use later. Now I will say k2 square is this term, people. What is that term? 2m upon x square into v naught minus e. Why? Because v naught is greater than e and k2 will be positive. Others, please tell me if you are understanding or not. This is important. There was a notification, so I'll switch it. Where is that? Hang on. So, see, if you would have assumed that this is k2 square, what is the problem? E is less than v naught. So you get k2 square is negative, k2 will become unnecessarily complex. But now as we realize, I've just taken minus common and I'm substituting this as k2 square and v naught is greater than e. Since v naught is greater than e, k2 square is positive, which is fine. I hope you understood why this. Tell me from.
Yes, sir. Understood.
Okay. So last time, definition of k2 had e minus v naught, now you have v naught minus v. That's the major difference. Next. So obviously the whole idea of the derivation changes after this. Okay. Copy this. Should I go to the next page? And you can always ask me to repeat. You can always ask me to repeat. D square psi 2 upon dx square minus. Now this whole term is k2 square. Okay. Into psi 2. This is 0. So people, we have got d square psi 2 minus k2 square psi 2. This is 0. Let's take d square minus k2 square common. I mean psi 2 common. This is 0. Psi 2 cannot be 0. It means d square minus k2 square. This is 0. D square is k2 square. What do we have, people? D is plus or minus k2. Real values. It's not complex.
Yes, sir.
Last time we had I k2. Now we have k2 people. So we have a real and unequal roots people. What do we have? Now we have real and unequal roots. We don't have complex pair this time people. That's the major difference. Okay. Real and unequal roots. Please tell me if you have any questions. Don't hesitate. Okay. So one root is basically k2, other root is minus k2. So whenever you have real and unequal roots, what do you write? How do you write the solution?
C1 equal k2x plus C2 equal minus k2x.
Perfect. So the value of psi 2, it is basically C1 e raised to people, whatever is the root m1x plus C2 is into whatever is the root m2x. But our m1 is k2 and our m2 is minus k2. So you have to substitute it accordingly. So C1 e raised to k2x plus C2 e raised to minus k2x.
C2 होगा.
That will make a correction. This is it. So this is m1 and this is m2. But C1 and C2 people are obviously already used, so we cannot use C1 C2 again. We'll make it C3 and C4. Yes. That's it. ठीक है?
Yes, sir.
Others, let me know if you're writing, please. Next, I'll go to the next page, okay? So let me just write. So this is our equation 2. Keep it in the box. Now I'll just write both equations again. So the value of psi 1 is C1 e raised to I k1x plus C2 e raised to minus I k1x, and the value of psi 2 is C3 e raised to k2x plus C4 e raised to minus k2x. Now is the period of our favorite part, because the way we have understood this will hardly be the way any other students of our age would have understood this. That is elimination of the constants. First of all, how can we eliminate things here? What is the method we can use here?
Put x equal to infinite.
No, we cannot do that here.
Complex है ना तो
This is
सर बोलो
complex.
नीचे वाले में कर सकते हैं ना.
हाँ नीचे वाले में कर सकते हैं. ऊपर वाले में people here, this is complex. Because it's complex, you have to take the plane wave equation idea. ठीक है? So in plane wave equation, if whenever you write that plane wave equation where psi is a e raised to I into kx minus omega t, so when kx is positive, like when you have I kx, it means you are moving along positive x-axis direction, and when you have minus I kx, like when you write I into minus kx minus omega t or omega t minus kx, basically whatever you write, I don't care. I mean, if you have minus kx here, in that case, it means you are moving along negative x-axis. Okay, however you write it. So the point is that, so since I have I k1x here, it means I'm moving along positive x. I got minus I k1 here, it means I'm moving along negative x. Now, does this make sense to us or not? That is what we need to check. This happens in region 1. So in region 1, along positive x, yes, that's incident. Along negative x, yes, that's reflection, people. So I can say, absolutely, this tells us about incidence. This is nothing but psi I, you can say, and this tells us about reflection, psi r. But when it comes to this, now when you have real values, I cannot use plane wave equation. It has to be complex. So for real, you have to use the definition of well-behaved wave function. Okay. Now the thing is, this is in region 2 now. Where is region 2? Region 2 starts from 0 and it goes until positive infinity. You know? Region 2 starts from 0 people and it goes until positive infinity. So you can say this is valid for x greater than or equal to 0. Check for boundaries. So basically there are two boundaries, 0 and infinity. If you substitute 0, do we have any problem? E raised to 0 is 1, e raised to 0 is 1, no problem whatsoever. So the lower boundary is not a problem. X equals to 0 is not a problem. But if we substitute x equals to infinity, the higher boundary of this, okay, then the thing is e raised to infinity, this makes it infinite wave function. This doesn't make it infinite. E raised to minus infinity, that is still 0. We don't care about 0. Wave function is 0. E raised to minus infinity, that is 0. If you substitute x as infinity here, you have minus infinity. E raised to minus infinity, that is 0. That's still fine. But if you substitute x as infinity here, this is making it infinite. That is not allowed. Wave function must be finite, people. It means this term cannot exist. Okay, C3 cannot exist. Our favorite part is the elimination part, and psi has to be only this. Make a note, please. I know that you have understood this already 2-3 minutes ago, but still I have to.
जो भी ट्रांसमिशन होगा वो नेगेटिव एक्स डायरेक्शन में होगा.
हाँ सर वो
no. This doesn't tell you direction, yaar. It's not
sorry.
I. It doesn't tell you
Yes,
direction.
yeah.
That's what. This is not a plane wave idea because we don't have I here.
I was getting confused there.
No, it's okay. It's okay. It's okay. It's better. And hence, I told you it's better that we discuss this again and again. So now that you have asked this question, now that you have permitted understanding, now you will remember. Okay. So you have to take it. You can always write only when I and minus I you can use the idea of reflection agents. Now I'm not telling you that this is traveling along positive and this is traveling along negative, not at all, because there is no I here. It cannot give us that information. Okay. So transmission could have been the addition of both. Okay. But the thing is, this is making it infinite. So it cannot be an addition of both. It is just this. That's it. So this is a transmission people. And it doesn't give us direction. It doesn't give us direction at all. Okay. This is just transmission psi t. Please tell me if you have any questions. Don't hesitate. And write it. This does not give you direction. It's not a plane wave. So I'm glad you were confused and you asked the questions. Take your time, please.
Yes,
Should I
sir.
write a book on pointer? Okay. So what do
Yes,
we
sir.
have people? Okay. But no, otherwise my classes make on writing up there. Okay. So okay, what do we have? Something in the chat box. Please, sir. No, I'm not writing up. I will only teach live. I'll be Walter Lewin types. Okay. If people want to make books, they have to record the lectures and create books out of it. You know, right? The Walter Lewin and then Feynman. Even Feynman you have heard.
Yes, sir.
His books is not something he has written. He has taken lectures in universities and people have recorded those lectures and they have typed the whole lecture. That's it. And that's how the book name is also Feynman's lectures on this, because those were actually the lecture recordings which we have just converted into words. But anyway. So
Feynman
finally
is
we have Hello?
Feynman is scientist, sir.
Ah,
Lecturer.
no, he was only author, but a very good author. Like you can also call it a famous scientist because he had a PhD, but I'm not sure about his major contribution to this, to be honest. But if you're a PhD, you're a scientist anyway, provided you're working or you're teaching, that's all correct. So even, by the way, if you're not aware of, you can call yourself a physicist once you have completed BSc. Physicists are basically those who have a degree in physics. So you are a physicist now. People write to be physicists, aspiring physicists. No, physicist means that you have a degree in physics. That's it. But then you can call yourself whatever you want. Anyway, so what is psi incident? We have an incident waveform. That's not incident. Now what do we have? Psi1. What is psi1? Psi1 is C1 e raised to I k1x plus C2 e raised to minus I k1x. And psi2 is C4 e raised to minus k2x. That's it. Okay? Now we need relationship between them. After this, you know the whole story. What we are supposed to do, apply boundary conditions, this, that, whatever. Should we do that or not? I'm thinking now. Actually, there is something called penetration depth in this, which I want to teach you. So in this, we can do a few more things. Okay? So let's start with relationships. Okay, let's say this is again equation 3, maybe equation 4. Let's apply boundary conditions and find relationship between C1, C2, and C4. Remember, this is an incident wave function, this is a reflected wave function, and this is a transmitted wave function now. This whole is actually transmitted technically. Okay, but the whole isn't if you had a C3 as well, but that got eliminated. Okay. So how to start? Boundary conditions. So what is the boundary condition? The value of the wave function at x equals to 0. It will be equal to the value of the wave function in region 2 at x equals to 0. Wave function must be continuous now. Continuous means that at this boundary that we have, here the wave functions must have the same value at boundary. Because it's continuous. Like here it may be like this, and then it may start decaying also, we don't care. But they are sharing the same point. They should be continuous because they must have the same value. Okay, so let's substitute. What do we have? C1 e raised to 0 plus C2 e raised to 0. This is C4 e raised to 0. Okay, so we just have C1 plus C2 is 0. Very easy equation. Say this is equation 5. Tell me if you're writing, thinking, processing, whatever. Okay. Actually, we should also be asking this. Are you writing? That's what we usually write. I should start asking, are you processing? Shouldn't we have written it? But then after that, they could be still processing. Okay, this is what is happening. Okay, so now this should be my new thing. I should start asking, are you processing? Okay, done. Now let's write equation 6. How can we find equation 6, people? Another boundary? Derivative. Okay. You are like now, sir, yeah, question? Difficult question. So now we know this.
Yes, sir.
Okay, let's calculate the derivative of. So what is derivative of psi1 with respect to x? So we have got C1 e raised to I k1x. C1 e raised to I k1x. Derivative of e raised to I k1x, that will remain I k1. But if you differentiate this, we have I k1 additional term. Similarly, we have got C2 e raised to I k2x. No, we have got C2 e raised to minus I k1x. C2 e raised to minus I k1x. So derivative of e raised to I k1x, it will remain this, but you have to redifferentiate this to get minus I k1. So we have got C1 I k1 e raised to I k1x minus C2 I k1 e raised to minus I k1x. We can take I k1 common. So if we take I k1 common, we have C1 e raised to I k1x minus C2 e raised to minus I k1x. What is the value of this derivative at x equals to 0? I hope you are comfortable so far. This is C1 e raised to 0 minus C2 e raised to 0. So we have got I k1, anything raised to 0, that's 1, we are left with C1 minus C2. Copy, please. Okay. Next. Similarly, let's calculate derivative of psi2 with respect to x. What will that be? Psi2 is this term, C4 e raised to minus k2x. That's it. Okay. C4 e raised to minus k2x. So derivative of e raised to minus k2x, that's e raised to minus k2x, but we have to redifferentiate this term that we will have minus k2. So we have got minus k2 C4 e raised to minus k2x. The value of this derivative at x equals to 0 is minus k2 C4 e raised to 0. So this is just minus k2 C4 e2. So let's equate the derivatives. Even derivatives should be continuous. So derivative of the wave function in region 1 at x equals to 0 is equal to derivative of wave function in region 2 at x equals to 0. Okay. So what do we have? Just a second. I k1 into C1 minus C2. Okay, and this is minus k2 C4. So we have got another equation, and that is C1 minus C2 is minus k2 upon I k1 into C4. Equation number 6.
minus 1 upon I को I कर दूँ.
Yes, absolutely. Minus 1 upon I को you can write I k2. Okay, next. So we have got C1 plus C2, which is equal to what? C1 plus C2 is C4. And we have got C1 minus C2, which is minus K2 upon I k1, minus K2 upon I k1, C4, which you can write minus 1 upon I as I, absolutely no problem. So I k2 upon k1 of C4. Okay. Remember, I can be written as minus 1 upon I, and minus I can be written as 1 upon I. You just have to rationalize it. Multiply divided by I, you'll get it. Okay. So that's C1 minus C2. So after this, we can express C2 in terms of C1, C4 in terms of C1. We can keep it ready. That again, we have JR, JT, that story people. That also we can process. But I think after this, I would like to jump. Now I would like to jump. So I want to teach you in this. Okay. So people, what is that thing that quantum was not allowing? In this case, sorry, classical was
Classical is
Classical.
transmission.
transmission. So we want to focus on transmission. Let's calculate probability density people. Okay, I'm jumping now. So I think that things are fine and time pass. Okay, R plus C will still be 1. Okay, it is the fact is not going to change. You can calculate R, if you calculate that is not going to change, and you can find that number to be 1. And you don't have to buy these things anymore now. But the point is, the kind of question that you can ask in this region, now E less than B is meaning the wave function. And other important part that is what we are doing now. Probability density in region 2. Why we are studying this? Because this is something which classical was not allowing, but quantum is allowing. Okay, so which is nothing but mod psi square if you remember, but you can write mod psi 2 square. Okay, mod psi square is psi star psi. Okay, so you can also write this as psi star psi, but it's actually psi 2 star into psi 2. So if you calculate this, what do we have? Psi 2, where is psi 2? Psi 2, psi 2, psi 2, where is psi 2? C4 e raised to minus k2x. It's real. It's real. There is no complex term here. So you can actually just write psi 2 square 2, and it's C4 e raised to minus k2x. Okay, so you can just write psi 2 square because it's real. But anyway, so what do we have? C4 e raised to minus k2x the whole square. So this becomes C4 square. You can write it any random constant, write it alpha, beta, gamma, whatever you want. Okay, e raised to minus 2k2x. E raised to minus 2k2x. Okay, so probability density people, as we understand. Okay, wait. Copy this. Let's call psi 2 as psi t now. That's transmission. Okay, so I'm just going to replace 2 with t because that's transmission. Okay, so what do we have, people? I would have copied this. Let me write it. Okay, so we have got psi t square. Wow, sorry, mod psi t square, which is probability density. Mod psi t square. It is actually C4 square. You can call C4 square temporarily something. Let's call it A, people. Let's call it A. Just random constant. And you can find C4 in terms of C1 later, but that's also not essential. So this is just a random constant A into e raised to minus 2k2x. Obviously, right now we are thinking, so what is the value of this constant? That also we can find. People, this is the value of psi t at this value of x. Okay, so we can use any boundary conditions that we know. Just so I can say psi t of x the whole square. Technically speaking, psi t which is a function of x. This is a e raised to minus 2k2x. Now, what happens when x is 0? Psi t of 0. Psi t of 0. This is a e raised to 0. E raised to 0 is 1. So psi t of 0 the whole square. That's a. You found out a now. A is a constant, people. So constant, what is the meaning of a constant? It's not a constant only at the boundaries. Once it's a constant, constant throughout. So you use boundary conditions to find the constant, but that constant is constant throughout the equation. So again, you can resubstitute this constant in the original equation because it's constant throughout. So if you substitute this again in the original equation, people, we have got mod psi t of x the whole square. This is actually nothing but mod psi t of 0 the whole square into e raised to minus 2k2x. This is the definition of probability density of transmission. Transmission probability density. First, to copy this. So what do we understand that probability density, people, is an exponentially decaying function. Probability density is an exponentially decaying function. Mod psi t x, mod psi t of x the whole square. When you write probability density, this is a constant, correct? It's proportional to e raised to minus 2kx. It's an exponentially decaying function. At 0, you will have some constant value here. The constant value at x equals to 0. What is the value at x equals to 0? Psi t of 0 the whole square. Okay, here you have psi t of 0 the whole square. That's the maximum value, and then it decays exponentially proportional to e raised to minus 2x. It means, what is the meaning of it? The chances that the wave function will exist deep into the position, people, like way far way ahead, that's difficult. Okay, so as the wave function goes ahead, you can say the probability of finding the particle keeps on decreasing and decreasing and decreasing. So it may be transmitted, but maybe the wavelength is continuously decreasing or something is happening. Okay. Probability of finding the particle immediately after the transmission, that is decreasing continuously. Hang on, a couple of more things in this. Take square root, people, on this equation. So what do we have? The value of psi t of x, that's value of psi t of 0 into e raised to minus k2x. Okay. So now I want to define something called as penetration depth here. Hang on. So penetration depth. It's very similar to skin depth thing you have learned in your EMT, people.
Yes, sir.
Okay. So it is basically a distance beyond which the chances of finding the particle becomes very small. Okay. Obviously, people, there is no specific distance as such because it's exponentially decaying. So you have to choose, like you have to define something, like when to quit. Like basically, what should be the maximum position until which we should look for the particle? See, tell me one thing. When you said that classical does not allow transmission to happen, but when you said quantum allows the transmission to happen, but if the transmission is going to happen, you have to look for the particle. Remember, what is the meaning of looking for the particle here? You cannot turn on the lights. So if you cannot turn on the lights, we will never know the path of it. Okay, so you have to observe in the darkness. So when you're observing in the darkness, how can we understand that the particle has struck somewhere? You have to place a scintillator, no? You have to place a screen. So like suppose if this is your region, people, this is a region. So somewhere you have to place a screen. Okay, so where should we place the screen? Should I place it here? Should I place it here? Should I place it here? The probability, obviously, where should we place it? People should place it as close as possible so that we will be able to detect it immediately if at all it happens. But if we place it far away now, there is high chance that we may lose the particle. It may be scattered, it may go somewhere else. So we don't place the scintillators far away. You have to place it close. Or you can keep a moving scintillator too. But the point is, there has to be a region within which you can expect for the particle to come. If the the particle is not reaching that region, people, after that you have to quit. You cannot just go ahead and look for the particle till the very end. You have to quit. You have to say that the transmission did not happen. This is nothing but known as quantum tunneling, people. Understand, even today quantum tunneling is still a mystery. We know that it happens. We still don't know why it happens. Why? The question mark why. It happens. It's a fact. Experimentally also proved, and let's say theoretically also understood. But why? The question. There are many things in physics where the question of why is still unsolved, people. How it happens we still know, as in the theory of it, the process of it. But we don't know that. Okay. And it's as good as why our existence, people. Why do we exist? As far as that's also the same question. But anyway, so quantum tunneling is an effect that happens, but why we don't know. Proceeding ahead. So the point is we have to choose an arbitrary distance. So we have used the idea which we have borrowed at many places where you talk about if you have learned LCR circuits and everything, there also you have learned time constant and things. So the same idea we are going to use here also. So for anything like this, like distance, time, what do we say? We use the exponent as the special number, people. So we say once the exponent value is reached, we will quit. After that, we are not going to search for the particle. So what you can say is here. So it is that distance. It is that distance.
It's the maximum distance.
Huh? No,
It's the
no,
maximum.
maximum would be the infinity, no? Maximum.
नहीं कहाँ पर chances है उसके हिसाब से predicted.
हाँ, we will quit. We will quit after that. Like after some position, we will quit. So what is that position you want to understand? Okay, so that is the maximum distance. Yes. So you can write maximum, but no problem. But maximum as in that would be misleading. Maximum could be infinity. But it is that distance beyond which, hang on, penetration data you already wrote. So it is that distance at which this value of psi t, people, it just becomes 1 by e times psi naught, initial value. Beyond this we quit. We have chosen exponent to be a special number all the time because most of our calculations, people, also they happen in logarithmic scale. In school you must have learned, or maybe 11th or maybe DSC, you must have learned how to plot a logarithmic graphs, not the natural graphs. Do you remember something like learning logarithmic graph scales where things increases massively, like 10, and then suddenly it becomes 100, and then it becomes 1000 in the same range, people? These are known as logarithmic graphs. So log helps to solve most of the mysteries and problems. As I still want to ask, have you learned logarithmic graphs?
No, sir.
I'm afraid not.
This is something you need to research. You need to learn probably today itself. Difference between normal graph and logarithmic graphs. These are very important things, like very important things in physics, especially when you draw graphs, people. So like for example, many times we don't have data of x equals to 2, x equals to 5, x equals to 10. We don't have that data. Suppose you want to study the whole thing, starting from x equals to 2 to x equals to 20,000. How can we do that in the graph? We cannot. For that, a special type of graph is made, which are known as logarithmic graphs. Okay, and this is the reason that we even consider this exponent as a special value, because the value of log e becomes 1. Once you play with log on both the sides, it helps you. The value of log e also becomes 1. There's a whole lot of theory that why exponent is a special number. But again, that's not something which we deal with in any of the books. It's something which you can learn out of your curiosity after your exam, people. Learn the importance of exponent. It's a very important thing. Okay, but learn about logarithmic graphs tonight only. Do YouTube, just search difference between regular graphs and logarithmic graphs. Do that. Anyway, so let's find the distance now. Okay, so what is psi t, people? Psi t is psi 0 e raised to minus k2 x. Psi 0 e raised to minus k2 x. Okay, here you have what? 1 upon e psi 0. Okay, I just substituted the value. So psi 0 gets cancelled. E raised to minus k2x. This is e raised to minus 1. So just equate the coefficients. What do we have? K2x is 1. We got the value of x, which is 1 upon k2. And in EMT also we have learned skin depth, which is the same thing. 1 upon k. So x is 1 upon k2. So this is penetration depth. Please learn logarithmic graphs today. But and learn the importance of exponent later. It's not immediate. So required. Okay. So beyond this distance, we will quit. We will stop expecting that the transmission quantum tunneling happened. If it has to happen, then we should be able to find the particle until this distance. Like from 0, you can write directly from x equals to 0, okay, to x equals to 1 by k2. To x equals to 1 by k2. Okay. We will keep searching the particles. Like we can place scintillator to detect the particle. We can keep scintillator to detect the particle. And beyond this, we will stop doing any efforts. Okay. Obviously, an optimist person would always want, sir, why are we not taking it beyond? Because people, it would be literally 1 in a millions of billion cases that beyond this exponent, you might get quantum tunneling happening. And that's too much of hard work. Okay. Beyond this, it actually doesn't happen. Okay. Exponent is a very special number. Next. Any questions, anyone? Okay. So penetration that we have covered. So people, in that graph also, as x increases, probability density decreases. As x increases, probability density decreases, and somewhere here, you stop. Like when x becomes 1 upon k2. Okay. After this point, we will stop. And this is the point. When the value of psi t x square, it is 1 by e. This is 1 by e of psi t 0. Okay, it's a different graph. Sorry, this is the graph that I have drawn here. This is the graph for psi t 0 the whole square. Make the correction. I think I wrote only psi t 0 there. Make it psi t 0 the whole square.
कर लिया था सर.
So just I will redraw another graph of only showing the wave function. Okay, the value of psi t x and versus x. Just showing the wave function. Okay. This is also exponentially decaying. Okay? The maximum value of the wave function is psi t of 0, and somewhere here, this is 0, let's say, where x becomes 1 upon k2, the value of psi t of x that becomes 1 by e times psi t of 0. And after this, probability becomes very negligible. Very negligible. We stop after this. Okay. So we complete this thing here. I would have loved to start with another barrier, which is rectangular potential barrier, but we'll now take it tomorrow. How many days do we have to
In total, how many regions are there?
regions as in how many cases we are planning to take?
Yes, sir.
So potential barrier, rectangular potential barrier we are taking, symmetric potential well we are taking. We'll take some random cases also which they have asked in the previous years, and hydrogen atom. That's it. So we have got tomorrow's day and day after tomorrow. So maybe what we can do is tomorrow and day after, and we may extend the class beyond 1.5 hour. Anyway, I have got the first class now. Okay, I will ask sir if he could interchange maybe day after tomorrow. Okay, but we will have the last class on Thursday only. I don't want to extend that for you. Thank you so much. We'll meet tomorrow.
Thank you, sir.
No problem.
Thank you, sir.
No problem.
Thank you, sir.
No problem. Shall I like this? Yes. Others let me try. Okay.